is Oskar Zieta. I come from Poland. I'm architect and process designer. I work in Poland and in Switzerland in the areas of processing, design, engineering, production and education. I teach at the ETH in Zurich and in very new school in Poland, in Poznań, School of Form. I am the head of industrial design. This is a very important area in Poland. We are producer from about 66% of, for example, IKEA product. And before I start to talk about the new method of steel stabilization, 3+, before I start to talk about our FIDU collection that we used as an experimental platform for different experiments in the geometrical solution, in the different materials, in the control of deformation. Before I start to go to the architectural scale, to explain how we use the FIDU technology in the architectural scale, before I talk about constructions, before I talk about precision in the FIDU technology and new standard that we can use in the FIDU technology, before I start about asymmetrical profiles and ultralight constructions and our work with different designers and artists, I want to, before I start to talk about the first rolled steel profile in the world that we present in the Victoria Albert Museum, before I start to talk about our space traveling, I want to go to our history. My grandfather was a blacksmith, and for me, there was the blacksmith 1.0. And after the industrial and technological, and for us, for the people from Poland, also sociological and political revolution, we try to be the blacksmith 2.0. Now I want to present you a small preview of our technology.
Normalnie projektanci projektują formę danego obiektu i próbują dopasować do tego technologię. W naszym przypadku my kontrolujemy procesy produkcyjne, a forma jest efektem tego procesu produkcyjnego. Nazywamy to procesem. Kiedy pierwszy raz widzisz produkt wygotowany w technologii FIDU, wydaje się tobie, że to jest miękki obiekt. W momencie, kiedy dopiero go dotykasz, to widzisz, że faktycznie jest napompowany, ale jest stworzony z twardego metalu. Proces produkcji to jest bardzo prosty. Wycinamy elementy z blachy, przy użyciu lasera, spawamy je szczelnie w konturze i pompujemy do stabilnej, trójwymiarowej formy. Praca w technologii FIDU jest jak rzeźbienie w glinie. Metal pod wpływem ciśnienia wewnętrznego formuje się w sposób naturalny i pokazuje swoją naturalną twarz. Dziś bawimy się i uczymy się w mikroskali budowania podstaw technologicznych pod dalsze aplikacje, które mogą być lekkie konstrukcje w architekturze, w przemyśle samochodowym, ale również i w kosmosie. I dzięki zastosowaniu konstrukcyjnym jesteśmy w stanie tworzyć lżejsze, ale bardziej wytrzymałe konstrukcje. Ja nazywam to mniej wagi, więcej możliwości.
All we need is less. But for us it's very important also to understand the difference between the mass production and the customized production machine. Of course, with the mass production machine technology, you can produce very quickly, very short, very precisely, but each time the same elements. And with the small one, much cheaper technology, you can, with customized technology, you can produce probably slower, probably not so precisely, but customized product. I think this is very important for us to understand, and and to work in the process. We need to understand also all parameters from the material which we work, and also the borders, production borders or limits, to involve all the parameters and the limitation to the design process. We start very smart, in small scale, and the objects and experiments was bigger and more complex. We design many objects they are produced and printed with the CNC machines, with numerical control machines, like this SXM pavilion from 2001 that we produce with our student in ETH in Zurich. There's manifest of N and Z construction system, and we designed this in computer and export to the laser cutter machine, and we never drawing all the 416 elements, and after we cutted this and bending, we put this together to this form, and we want to present that we can produce in this system straight way, we can straight wall, we can go through the make different edges and also three-dimensional shapes, forms. We made many experiments in this area, and each time was this the process was very important for us. We work on not only in a metal sheets material, but also with different profiles, with different materials. Like here in this project, we had only 3 parameters to describe the form. The programming is there, and the 3 parameters are only the length of the profile, the rotation, and the angle. And we design this form from the computer on and produce this. Very important for us is the work together with industry, with experts from different ways, from the material way, from the industry that produced the machine like this. We understand, we work with this machine, we try to understand the limitation of the technology. We try to understand what is the tool, what can make the tool, and how is the stabilization process and involve the knowledge to the computer. And after we produce the elements very precise and real and put together to many different constructions, semi-transparent walls, ceilings, and facade elements. Much of this is also produced in real scale. In this course, we develop also new technology. We call this 3+ technology. We go from simple point, we deform this point and we make this point stable, and then we can make this in different matrix and stabilized the whole metal sheets, sandwich plates, to make different design, to be much flexible in design, to involve this process or the system to small workshops, to the office, but also to the home. Very important for us is also the construction part, to understand what is how durable we can produce ultralight construction. And we made many courses with our student and also with the expert from IBK Institute. They are Bauingenieur, building engineers. And of course, in this course, we understand that the building engineers not really understand what is the very thin material, how to work with ultralight construction. They know, of course, to work with standard profiles, but they have not really idea to work with FEM systems, simulation systems, and so on. And after this course, we are going to automotive industry. For example, this construction, the engineers are calculated for 60 kilos, and this construction takes more than 1.5 tons. We're going to the automotive industry, and there we find IHU-Verfahren, IHU technology. This is hydroforming technology. It's a very beautiful technology. In this technology, we can produce very precisely elements, constructions elements, very complex form. But the problem is, of course, for us, for architects and for designer, this technology is very expensive. You need very expensive machines. They are not everywhere. And you need very expensive tools. For example, for these elements from Opel Meriva, you need, there's only 3 meters long, and you need, for the tools, only for the tools, 2 million euro. And of course, I give up everything what is expensive. I give up the expensive machines and also the tools. And everything what I need to and I use to the FIDU technology is the material, is metal sheets material, and the inside pressure. And of course, the technology, but flexible technology, laser technology. And in the first experiments, we tried many different geometrical forms to understand what is the language of this technology. We tried more than 100 different experiments, different forms, to make something like FIDU alphabet. And now we know, and for our design, we can use different letters to produce, to design beautiful shapes, forms. We developed something like FIDU alphabet, and we use this now already to design our products. And very important for us is also in the last 12 years we tried every time we tried to design also the process. And we see we can involve today all information from the material and import this to the computer. In computer we can make designed and made simulations of the three-dimensional form, and then put to the two-dimensional material and cut this with the laser machine. And then with the same tool, with the laser, we can weld it in the edges, the two of material of the shapes. And then until this point, we work very precisely, with a precision of 0.2 millimeters. And until this point, we call this controlled loss of control. This is the most interesting part in this technology. But what we do is today, or was, is like error, is defined in the DIN norm, is the German engineering norm, like an error. And we work with the error. Also interesting is this part that we are not really designer of this end, of the final form. We are designer only from the 16 kilobytes of the product. And of course, and the material and the process made the end form, the final form. And to describe this final form, we need, in the same precision, we need more than 142 gigabytes of information. I call this, this is simplicity in design. This is process design. And we try to use this technique in different materials and produce different form. Very important for us is also that we design mass production process. But each element that is produced in the process is unicat. Of course, we can, when we transport our product, for example, to India or to Australia, we can transport this in the flat form. And this is exactly the same 200 elements in the one in the car, and they are blow up, they're in three-dimensional form, and the same part of elements in the very important for us, or that we is also that we are very stable. What do you think? How many kilos can take this small stool? They are only 3 kilograms heavy, and there is made from 0.8 millimeters material. It takes more than 2 tons. We made this we need to have the test for the American market, but we need only 400 kilograms, and this construction is much stable, much durable, and of course ultralight. Made in aluminium is only 1 kilogram heavy. Of course, we used not only simulation process. For our design process, we use also try and error method. But we can also simulate it, our form, and then produce this in different materials. We learned this technology, and for today we can produce not only manifest like the plop or like the chip and steel chair, but also very precisely elements like the Unterdruck bench. But also in the very precise and minimalistic form, they are very, very stable and durable. We produce many with interior designer, many elements, walls hanger, but every time very important for us is to connect this with some engineering point, like for example with this hanger, we use the design, we use the knowledge that we find in the design process, and we use this, for example, here for the ultra light blades for the wind turbine. Very important aspect for us is also the XL scale. This is the architectural area, and here we can present what is our standard. Everything what is designed conform in our language, in FIDO language, in FIDO alphabet, and we can place on the metal sheets plates is our standard. It's different like the standard profiles the engineer, building engineer are used. And of course you can transport this in a flat version, in a flat form, and deform on the final destination. Of course, we understand very quickly that we produce ultralight construction, and the first idea to produce a bridge in this technology. We find this in 2007, and we produce a bridge that is 6 meters long, 1.5 meters wide, and only 170 kilo weight. We tested this, and the solution was to take more than 1.85 tons. Of course, all engineers say, okay, Oskar, you are stable, but you are not so precisely. Not so precise. Of course, we take this thema and we designed Fußball, das Icosahedra, that is made from 19 same elements. And in this project was very important to work very precise. After this, we produced some fair constructions for the architectonic platform. One element was ultralight construction, something like not 46 kilo wide, and you can put this together in 3 different possibilities. We work also together with different artists and designers, like for example this structure that we made together with Eric Levy. And now we are by this project. This is the I think very important topic for us. This is the Volumenexpandierung or expansion. And we are involved in the exhibition by Victoria and Albert Museum in the Madejski Garden, inside of the museum. The problem was to transport our ideas inside to the Madejski Garden, but all doors, entries was only 1.50 meters wide. And we decided to make this exhibition. We call this blow and roll, and we connected here the engineering and art in one project. And that is the first rolled steel profile in the world. And you can deform this with a normal bicycle pump. It's no trick. I have also here one profile with me. And you can see and now in a very quick way I produce small ultralight constructions profile. The exhibition we transport this in small rolled form to the Madejski Garden, give the direction and blow up. The biggest one was 30 meters long. And we looking for new application, like for example the crash barriers in the highway or other underground constructions, and of course for the Swiss people. And we go with this technology, we go already with Professor Kabacik from Wrocław University to the space. We try to develop some new construction for the antennas, for the space antennas. And I think this is only the space is now the limit for the FIDO technology.